Okay, in the next lecture today, ladies and gentlemen, we're going to be talking about the strengths of acids and bases and how we calculate strength of acids and bases, okay? So, first of all, we have to come up with some better terms because concentrated and dilute are really not so good. We need to be thinking about strong and weak because when we have a strong acid, concentration is the same because it completely dissociates. But when we have a weak acid or base, you know, that's a misnomer because, to be honest with you, the amount of acid or the amount of base that's dissolved in solution is very, very small. So it's really dilute in some respects. So be really careful about the terms concentrated and dilute when we talk about acids and bases because the amount of H plus or the amount of OH minus or that is present in solution is what determines the acidity or the basicity of a solution. And so if you have something that is weak, then you're not going to have very much H plus or very much OH minus dissolved in that solution. And so using concentrated and dilute is really hard when you're talking about those things. So just be really careful about those terms. So we want to talk about this amphoterism of water really quickly. This idea that water can be both an acid or a base. And that in actuality, water does we call auto-ionizes in a equilibrium expression. So, you know, it doesn't do this a lot. So how do we figure this out? Well, we know that it's temperature dependent. So at 25 degrees, the Kw is 1 times 10 to the negative 14th. That means the components that make up water and water's dissociation, Kw, right, goes to 1 times 10 to the negative 14. So that's the concentration of H plus and OH minus in the solution from 2 molecules of liquid water dissociating, okay? So let's just think about that for a second. That's not very high. That's a very small number. So there's a very small amount of dissociation going on in normal water. And clearly temperature affects it because we can see as we go from 25 to 95, the Kw decreases some. It gets a little bigger. So that means that there's more ionization at higher temperature, and we get that. That kind of starts making sense if we think about it from terms of what we've been talking about all along. So this was developed by a brewmaster to test the acidity of beer because remember, you know, you want beer to be nice and mellow and it's got to taste good and all this stuff. So this guy came up with this scale and this idea of pH and pOH. And here are the formulas for that. pH is the negative log of the H plus ion. pOH is the negative log of the OH minus ion. And in reciprocal, just to let you know, if we were trying to find the concentration of one of these, let's take that. The equation for that would be concentration is equal to 10 to the negative pH value, okay? And when we do that, we're actually doing an exponential, you know, it's basically opposite. So when we have LOG, this is the opposite. When we have LN, we know the opposite is E. So just to let you know mathematically. So this will be used as well. So you need to make sure you understand that. And if you look on your calculators, they're together. On your calculator, you will find an LOG button, and the second function key is the opposite of the LOG. On the LN button, you'll find the opposite of LN. So those keys are put together for very good reasons. So make sure you know how to use those. Okay? So what do we know? Well, we know that the pH of a system of water is this. So we get this equation, right? We're looking at the equilibrium expression equation. Why is there nothing on the bottom? It's because these guys are liquids, so all that matters are these. So we get 1 times 10 to the negative 14th is equal to x squared, so x must equal 1 times 10 to the 7th. Well, if we take a calculation of pH, we get 7 for the pH and 7 for the pOH. They're neutral. Water's still neutral, even though it ionizes some, so it's all good. We make equal amounts of each of those things. And this idea that we have 7 and 7, this idea of 14 is going to be really important because we can go back and forth between pH and pOH. So for example, if we're given the pOH and we want to know the pH, we just take pH is going to be equal to Oops, sorry about that. Crazy stuff going on here. All right, pH is equal to negative, well, back it up. Okay, so pH is equal to, let me erase that real quickly. pH is equal to 14 minus the pOH. And the opposite is true. pOH, I'm sorry, I can't write because it's not, I'm running out of space. I'm off the chart there. So, and the opposite is true too. So pOH is equal to 14 minus the pH. So that's always something really great to know. So here is that information. And you can see here. So the difference between pH and pOH, you see it right there, right? Okay, the difference between the pOH and the concentration, well, you can see going from the concentration to the P of it is the negative log, and going from the P of it to the concentration is times 10 to the negative pH, okay? So just make sure, and then up here, we have these calculations based upon the kW value, and 1 times 10 to the negative 14th being the kW. So basically they're using the equation, let me get a different color here, they're using the equation kW is equal to the concentration of H times the concentration of OH, okay? And so that's the rearrangement of this up here. So going between those two is based on this equation about the kW water. And we're always using 1 times 10 to the negative 14th. That comes in handy quite often, okay? So this idea that water has both natures, we can see that. This idea that it's an equilibrium, because it is, it's really, really small. And that's where we get the pH, that it's neutral of water. And then everything else goes from that perspective. And remember, this started out with a guy who was actually making beer, okay? So, acid, base, or neutral. Basically, if you have a pH that is less than 7, it's acidic. If it's more than 7, it's basic. If it's neutral, it's 7 at 25 degrees Celsius. It'll be a little different at different temperatures, but we're normally working at 25 degrees Celsius, right at room temperature, so that's all right for us. So you can also compare the concentration. So we can compare the pH to determine if it's acidic, basic, or neutral. We can compare the concentration. If the concentration of H plus is greater than OH, then it's acidic. If the concentration of OH is greater than H, then it's basic. If they're equal at any temperature, it's neutral, okay? That's pretty easy to think about. So how do we solve some problems? So here, what is the pH if the concentration of H is? Well, that's pretty easy. Remember, pH, here, let me change colors again, sorry. Need a brighter color. pH, I don't like that. I'm being picky. It's all right. I can do that. I'm gonna get green, I like green. Okay, pH is equal to the negative log of the H plus concentration. So that means it's the negative log of 4.5 times 10 to the negative 6. Okay? Then we just do our calculation, and when we do that calculation, what we end up getting is an answer of 5.3. It's just plug and chug from that point, okay? And I believe some of these equations are on your green sheet, if I'm not mistaken. So I'm looking for one really quickly. Give me, nope, that's not the green sheet that I was looking for. I may not have one up here right now. Oh, yes, I do. Let's see, thermodynamic gases and liquids, Faraday's constant, equilibrium kinetics. Oh yeah, under equilibrium, you will see all of this. You will see pH, you will see pOH, you will see 14 is equal to pH plus pOH, we will see pH is equal to pKa plus the log of, and you'll see what that is, and pKa minus the log of Ka, etc., etc. So all of these equations are actually on your green sheet, including Kw, okay? So lots of information on the green sheet about acids and bases, because we're talking about equilibrium in a lot of respects, especially when we have weak acids or weak bases, okay? So next question, what is the pOH if the H plus ion concentration is 1.5 times 10 to the negative third? So again, we go and we find the pH. pH is equal to the negative log of the concentration, 1.5 times 10 to the negative third. And when we calculate that, we get an answer of 2.8, but that's not POH. So if we want POH, POH is equal to 14 minus 2.8 minus the pH. And so we get an answer of 11.2. There's the POH of that substance. Okay, what is the H plus if the pH is 4.63? Okay, so we've got to go back. Now remember, we've got some equations, but it doesn't tell us exactly how to do this, but our calculator does. Remember, the log is below the second function key is times 10 to this, so we know that the concentration of the H plus is the opposite, so it's 10 to the negative pH. So if we start plugging that in, we have 10 to the negative 4.63. And all we do is press it on our calculator. Press the second function key and the log key, which gives you the 10. Then you press in negative 4.63. And when you get that, you get the concentration is 2.34 times 10 to the negative 5th molarity. It's that simple. It's just a calculation, okay? So what is the pH if we have 12 molar HCl? Well, we've got to remember something. HCl is a strong acid, which means the concentration of H is right there. It's already listed for us. So we know that the pH is equal to the negative log of 12. And this is really interesting because we're going to get a negative pH value. So hydrochloric acid in high concentrations is highly acidic. Anything that is obviously less than 0 is pretty acidic. So yes, you can get negative pH values. So, make sense? All good. Thank you.